5, and it's in the blue packet, and it's on. I was so excited about St. Patrick's Day. I was thinking green. Oh man, I gave you guys 5 minutes. Come on. So it's blue. We're going to talk about Tone's test, Benedict's test, not today. We're going to talk about optical isomers. Speaking of Toland's test, we did that making ornaments for Christmas. All right, stereoisomerism. First of all, there's 2 types. Let's zoom up on this. So this is the second page right after part 5 starts. So stereoisomerism, what we got is molecules that have atoms attached together in the same order but differ from each other in their spatial 3-dimensional arrangement. So in 2D, they're going to be written pretty much the same, but in 3D, you're going to see distinct differences. So there's 2 types. One we talked about, which is called geometric isomer, and that's the cis and the trans. Cis-trans. Cis means it's like a field goal, and trans is walk like in a deer. There you go. But they're basically in 2D, they're going to look very, very similar. You're going to have the same carbon bonded to this carbon in both cis and trans. The difference is the conformation based off the electronegativity, repulsion of the electron groups. Number 2 is optical isomers. We haven't talked about that yet, and that's what this is organic in terms of isomers, and this is the focus for this week, basically. They're mirror images, and we've got 2 right here. Well, it's kind of hard to see. Put it right there. So look at that. It's like looking at itself in the mirror. You got white to white. The tops are greens. The backs are blues, and the fronts are reds. But if you try to put it on top of each other, you got red where blue is. That is a different type of molecule. So these are switched. So they are mirror images of each other, and they're non-superimposable. I can't put it on top of it and be the same. It's kind of like your left hand and your right hand. You try to put it on top, and it doesn't work. The thumbs are on opposite sides of each other. So this is an analogy of optical isomers. They're mirror images, but non-superimposable. So, is there going to be a large difference in their chemical properties? Significant difference, yeah. So this could mean the difference between you, if you're pregnant with morning sickness, having it alleviate your morning sickness, or having your child come out with, like, mini arms. Yeah. And this was a problem in the 1960s. Oh man, they were called flipper babies. Where we got it? Let me get it right. Yeah. Thalidomide. Where is it? Oh. Oh, yeah. Thalidomide. There it is. Thalidomide, yeah. So, basically, the big pharma at the time just kind of said, oops. So, I'd have to look into, I think there are some lawsuits, but...
I think there's still people alive with us.
Yep. So, permanent.
I kind of want to say it.
So, and it all has to do with the molecule being the wrong isomer, the wrong optical isomer. And what happened was the thalidomide that was given in this morning sickness pill was a mixture of both of them. And back in the day, they were like, oh, thalidomide. So, but there's 2 different types in there. And now they do have a process where they can separate them. And it's relatively new. Like, well, now it's 20 years ago. I guess it used to be relatively new. I guess it's getting kind of far away now. Asymmetric synthesis was developed, which process for manufacturing a single enantiomer using a chiral catalyst. So basically you can... So it's almost to the end. So you can easily make both isomers, but now they have a different different methods to be able to isolate and produce just one isomer. So yeah, the different products have unique physical and chemical properties and can therefore be separated. Resolution is the process of separating two enantiomers from a racemic mixture. So with everything that's pharmaceutical, it usually takes 8 to 19 years from conception of idea to marketable sale of drugs, and then it has to go through all this approval process, FDA approved. Even then, you can have some, side effects that are unforeseen. So big pharma is always doing experiments on the human population, so legally. Moral of the story: if you can avoid pills and medicine, do it. So, but sometimes medicine's important; you got to take it. Because the more you put in your body, the more things that can happen. Okay, here's some terms. A racemic mixture is a mixture of two optical isomers. And we're going to be doing a polarimeter lab. I think we only got 3 because one doesn't work, unfortunately. They're like $500 a piece, and it's kind of annoying that they just break that easily. A polarimeter. What a polarimeter does is it takes a liquid sample of a optical isomer, and it's going to refract light one way, whereas the other optical isomer will refract light the other way. And this polarimeter can identify that. If you got a racemic mixture, they're going to offset each other, and it's going to be no change, no light refraction. And so, what I believe I have limonene from oranges and then limonene from lemons. They're both limonene, but they're opposite. They're optical isomers of each other. One smells like lemons, one smells like oranges, and that's pretty much the main difference for limonene. And we're going to just kind of look at those in these polarimeters to see if it actually does a difference. There's another lab, we just don't have a lot of time. Maybe we could pull it out after the IV test. That just looks at the concentration, because it's kind of complicated. So you almost need to do like 3 labs to figure out how to use a polarimeter. So we'll try it out. We'll see. Maybe we'll take 2 days with it instead of 1. So, but I've always done the concentration lab in the past, but that doesn't get the idea of, well, one isomer versus the other. It just looks at the idea of different concentrations and how that impacts the polarimeter, because it does, and it's something you do need to be aware of when working with that. Oh, here, we're talking about smells, oranges and lemons. You got the plus versus the minus optical isomer. Taste buds on the tongue and sensory receptors in the nose contain chiral molecules and so interact differently with the different enantiomers. That's why we can identify lemon smell versus orange smell, because of those sensitive receptors on our cells. So the human body is extremely, insanely complex. All right. So that's that. So that's kind of the macro idea of optical isomers. All right, so here's a nice little flow chart. Flow charts are kind of nice to organize them. You got this main word, isomer. Isomers are just things that have the same chemical formula but different orientation of those atoms. Hey, there it is. Same formula, different structures. There's 2 big categories. There's constitutional isomers, which is the thing we talked about with alkanes, how pentane could have an alkyl group. It could be a butane. Yeah, pentane could be a butane with a methyl group hanging off. Or it could be a propane? No. Or propane with an ethyl, which is still butane with a methyl. Yeah. Well, anyways, those are 2 constitutional isomers. I think there's another one. We'd have to write them out. And then the other one is stereoisomers. And this one can be broken up into a couple things. With a stereogenic center. These are chirals and no stereogenic. All right, so let's see, no stereogenic. Okay, yeah, so this would be geometric. So you got the geometric isomers like the cis and trans, and then you got the optical isomers that have a chiral center. So stereogenic just means that you have at least one carbon atom that's bonded to 4 different things. So this one is blue, white, red, green, 4 different molecules it's attached to. So this is chiral, this carbon atom. So basically, could you be an optical isomer if you just have 3 outer or terminal atoms attached to it? The answer is no. You got to have 4. So and that's why it's unique to carbon. You're not going to have any other molecule that's going to form an optical isomer. So that's why it's unique to biochemistry and organic, because that's what carbon is all about, organic chemistry. So then you got enantiomer and diastomers. And enantiomer is what we're going to be focusing on in this class. That's what this is. You got just one chiral center. Diastomer is, they're non-mirror image isomers because they have 2 or more chiral centers. And that's when you get into more complex biomolecules. So pharmaceuticals is super complicated, and that's why you try to get a drug that helps people, and then you get all these oopsies. Sorry, I didn't mean to do that, but you can't sue us because we're protected. So. All right. So geometric isomers. Question? Oh, no. Oh, yeah. We got cis versus trans. You guys kind of know this. Which one would be cis? Oh, it says it.
I thought you were for real. I was like, oh.
All right. So we know this is cis because it says it's cis. But you got these coming out at the same direction. And typically, if it's black, solid, it's going into the page. And if it's dashed, it's coming out of the page. So here we got one going into the page and one coming out. So that's trans. Opposite sides. Here it's same side. And then with the long biomolecules, here it looks like this is a carboxylic acid, COOH. It's also an alkene because it has a double bond. And here's trans, where they're all far apart from each other. And here's cis, where there's a kink in it. And this is a little bit closer to that group than this is to that group. So, basically, this fatty acids are triglycerides, and they have a fatty acid chain, so a long chain of things like this. And when you have trans fat, that means you've got kind of the more double bonds. If you're a saturated fat, then you have less double bonds because it's saturated with hydrogen. So that's the difference between trans and saturated fat. Has to do with the structure.
Why is trans worse for you?
So trans is worse. The reason is your body just can't process it. So it just kind of, if it doesn't stay in your body, then it kind of just goes out. Yeah, it's trans. Yeah, mainly your body just doesn't process it. So can you eat trans fat and live? Probably, yeah. But could you develop cancer if you eat it more? Probably. Yeah, I think they're trying to get rid of trans in the diet, and that's why like Miracle Whip just doesn't taste good anymore. So. My aunt was really upset. She's a good cook, and she was saying the recipe's just not good anymore because she always uses Miracle Whip. But if trans fat was truly bad for you, then they wouldn't be allowed to have it. So like it's, I don't know. They have, it is, yeah. They've got evidence suggesting it's bad, but it's not strong enough. So, okay, here's something new. Physical properties of geometric isomers. That's a cis-trans. So cis transformation changes physical properties. Physical property, that's like what? Melting point, boiling point, stuff like that. Cis formation will usually have a higher boiling point. So cis, higher boiling point. Due to stronger dipole moment, more polar. Okay, here's trans. Okay, looking at this example right here. We got trans versus cis. This definitely has a stronger oh, we can't see that. All right, here we go. So this definitely has a stronger dipole moment because you got both electronegative entities on the north side, or the top, of this molecule. Where here, the dipole moment is basically a moot point because they, balance each other out. Going there. So this has an actual plus or minus charge, partial. So it's more polar, so therefore it's going to have a higher boiling point because of those intermolecular forces. And this is going to have what type of intermolecular force? It's going to have dispersion for sure, and dipole, you got it. Because of the polarity, polar molecule is going to have dipole. Is there hydrogen bonding here? Is there any hydrogen bonding? So the FON group, F-O-N, nope. There's no FON group here, so it's chlorine. So no hydrogen bonding, but it is dipole. This one has, well, this one's symmetrical, so therefore we could consider this nonpolar actually. Therefore it's just going to have dispersion forces present. So that's why the boiling point's higher, because there's stronger intermolecular forces. All right. Transformation will usually have higher melting point. All right, trans will have higher melting point as it packs more easily into a solid, as it is more symmetrical. Intermolecular force is more effective. So it's going to stack like a chair, like this one. Here's an example. That would be like cis, and here's trans. So which one has more dispersion interaction? Definitely this one. These might have dipole-dipole interactions, but when you're talking about turning into a crystalline solid, it's going to be the transformation, conformation that, the transconformation. That's going to have a basically higher melting point because it's going to take more energy to disperse those dispersion forces or break them. All right. So does this have a higher or lower boiling point? Higher. And then trans has a higher melting point. Yeah. All right. Oh, we're still talking about geometric isomers. All right. Cis-trans chemical properties are usually very similar, although in chemistry there are always exceptions. So we're not going to really get into the differences in the chemical properties because of those exceptions. But here's just an example. Heating cis-butadioic acid forms butadioic anhydride in water, whereas heating trans-butadioic acid sublimes it with no chemical change. So, and is there going to be different chemical properties for every type of molecule? Yeah. So don't have to worry about that. Just know that chemical properties between geometric isomers will be different. That's just kind of showing it. All right, geometric isomers, cyclic molecules. So here we got the picture of cis versus trans. This becomes very, very important when we talk about biochemistry because sugar is basically a hexagon with a couple of carboxylic acids and alcohols sticking off of it. So this is carbohydrate chemistry right here. Oh, speaking of it, here it is. Sugars, and there's fructose, which is 5 carbons, and glucose is 6. And we'll have like, I think 2 or 3 weeks to talk about biochem after the test. All right, here we go. Finally, optical isomers. A carbon atom attached to 4 different atoms or groups is known as asymmetrical or chiral.
Oh, wait, nothing to fill in.
There's nothing to fill in. It's apparently already filled in. I'm helping you out here. I think this was probably the answer sheet, and I actually put it into that. Yeah. All right. So the 4 groups arranged tetrahedrally. 109.5 angle can be arranged in 2 different 3-dimensional configurations, which are mirror images of each other, just like that. And it's really hard to see, even in a picture. That's why if you want to pass this around, you can kind of look at it. They're mirror images with each other, but once you put it on top of it, you can see that it is actually slightly different.
Boom.
All right. The term chiral in general is used to describe an object that is not superimposable on its mirror image. It's the adjective, whereas an antimer is the noun. Thinking a little bit of English class here, is one of 2 stereoisomers that are mirror images of each other. They're not superimposable, not identical, much as one's left and right hands are not the same except for opposite orientation. So an antimer is the noun, chiral is the adjective version of that noun. So you could say those molecules are enantiomers, which would mean that they are quite chiral. Chiral being an additive. Oh, there's Sally saying hi in Intimer. But if you put Sally on top of herself, she would not be the same person. So these are pictures of hands. They're mirror images of each other.
What
Hands, you know. It's a picture of hands. Either that or they're like cloves of garlic. One of the two.
Wait, those are hands? They're gloves. Also.
Gloves. That's what they're supposed to be.
Oh.
So they're mirror images, but non-superimposable. All right. Racemic mixture. I mentioned it. Anybody know what a racemic mixture is? It's when you got a mixture of both optical isomers. So a mixture containing equal amounts of the two enantiomers. And optical isomers have identical physical and chemical properties with two exceptions. Optical activity and reactivity with other chiral molecules. So what is optical activity? That's what I was talking about with the polarimeter. What it does is it measures the basically the angle in which it refracts light. So one will refract it a certain angle one way, and the other will refract it a certain angle the opposite way. And if you got both of them together, the polarimeter will identify no optical activity. So basically refraction of light, and then reactivity with other chiral molecules. So just like thalidomide created birth defects, one optical isomer, and the other one created or got rid of morning sickness for a pregnant mom. All right, optical activity. So focusing more on that, optical isomers show a difference in a specific interaction with light. Ordinary light consists of electromagnetic waves that oscillate in an infinite number of planes at right angles to the direction of travel. So, trying to show that, you've got light going at you this way, at this way, at this way, at this way. So it's hitting you at all directions. And what a polarimeter does is it cuts out the noise and it only allows one plane of light of direction to come in. And that's what's going to be refracted by the optical isomer. So see how you got like a whole bunch of different planes coming in, and then it's just flat, just one plane. That's polarized light. And if you wear sunglasses, that's kind of what it does, is it blocks out a lot of the different angles at which it's coming in and just gets one angle. So it's shaded, essentially. If the light is passed through a polarizer, only the light waves oscillating in a single plane pass through. Light waves in all other planes are blocked. Questions on that? All right. Yeah, actually there's a couple of videos. Light that passes through a plane is called plane polarized light. Similar effect is achieved with polarized sunglasses.
A sodium lamp emits nearly monochromatic yellow light. The light is not polarized. That is, the electric vectors of the light vibrate in all planes through the direction of propagation of light. When a sheet of Polaroid or special polarizing crystal is inserted into the non-polarized beam, only light that moves into a single plane passes through. The light is said to be plane polarized. When a second polarizing element, called the analyzer, is placed into the beam, the light is transmitted fully only when the analyzer and polarizer are aligned. As the analyzer is rotated from the aligned position, the transmitted light decreases and is blocked entirely when the polarizer and analyzer are 90 degrees apart. When we place a tube containing a solution of non-chiral compound in the path of the beam, it has no effect on the plane of polarization of the light. However, when the solution has an excess of 1 enantiomer of a chiral substance, the plane of polarization of light is rotated. Because of their effect on polarized light, chiral molecules are said to be optically active. The 2 enantiomers of a chiral substance cause rotation of the plane of polarized light in opposite directions.
Short and sweet and to the point. I think that's how I got it labeled too. What's that?
So is that like sunglasses? Like
Yeah.
the lens thing? The plate?
Yep. Sunglasses are a basic version without the optical isomer.
What about like the ones that are Chiral? What are they called?
Well, those are actual lenses.
Oh,
So
okay.
sunglasses are just they're,
Okay, I
you can
see.
see through. They don't impact your vision. It's just
So
they
the
shade.
plate can be transparent.
yeah.
Oh.
Yep. All right, we got another.
Let's make fun of Brady because he's stupid. Just kidding.
Oh. That looks pretty.
Here, we'll pause this for.
What happens when I introduce some of that enantiomer, that D enantiomer of my compound? I will observe a rotation in the plane of polarization, and the amount to which it rotates can be calculated. So this new plane of polarization will depend upon three factors.
We're gonna see this in the lab, and it's kind of a little
First,
complicated.
the specific rotation of
Not
the
an IB
compound.
requirement.
This is a measure of how well the compound rotates plane polarized light and is an intrinsic property of the compound, just like our extinction coefficients in the previous example. The path length is also considered. And the third factor affecting the extent of the rotation is the sample concentration, which I've labeled here as C sub dex, meaning the concentration of the dextrorotatory enantiomer of my compound.
All right,
So-
that's why one of the labs, we're going to skip it this year, so we got time to actually just look at like lemon oil versus orange oil to see where it rotates. And we're not really going to focus on this math, but sample concentration is huge. Whenever you're comparing, you got to have the exact same concentration. Otherwise, that's going to impact the plane polarized light. All right. Here, I just want to talk about multiple chiral centers real quick. Because we're done in 4 minutes, right? Yeah. All right.
That was one of those moments that I actually did. I was like,
All right, here we go. Multiple chiral centers. If we look at this, right there, that's a carbon, and this is a carbon. We've got bromine, methane, hydrogen, and a carbon. Hey, that's 4 different things. So right here, that's a chiral center. What about this one? We got chlorine, methane, H, and a carbon. That's also a chiral center. So in this class, you're not going to be dealing with diastereomers. We're just talking about them. Since we're on the topic, can you have more complex enantiomers than something with just one chiral center? Yes, you can. We will be looking at molecules and trying to determine if it has a chiral center or not. And the key is there 1, 2, 3, 4 different things that it's attached to? And if you can say yes to that, then it is a chiral center. Whereas if you got something like C, H, C, I don't know, something like that. This thing right here, we got a carbon-carbon, that's the same thing. Or HH, that's the same thing. So this is not a chiral center. It has to have 4 different things attached to it. And when you have more than one chiral center, now you have more than 2 optical isomers. So you've got this variation, that variation, that variation. And you might be able to have a few more, and it gets the amount of organic molecules or optical isomers exponentially increases with each extra optical or chiral center, which is why biochemistry is kind of so difficult, and why you can have like millions and millions and upon millions of different types of organic molecules, including amino acids, and it just makes it so complex. So everything that happens in a cell, all the reactions, there's so many reactions, we don't really know all of them. We don't know most of them. Which is why when we have new drugs, there could be a lot of adverse reactions to those. So, diastereomers are stereoisomers that are not related as object mirror image and are not enantiomers. So they're not mirror images, but they do have chiral centers. So Requires the presence of two or more chiral centers, have different physical and chemical properties, and may be separated by physical and chemical techniques. So there it is. Tomorrow we're going to do work on the worksheet on optical isomers.